when I'm in a drop top. Da, 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 da.
Hey, that's out of order.
Who did that?
I think we should restart this one.
Remind me last time, Dom, I'm going to have to do a voiceover on that last one.
I think that's Taylor's
I'm
fault.
blaming
Taylor
you.
did.
Oh, yeah, that's it.
Right.
Blame on me.
So the first thing you said you was going to do was find
Excel.
Excel, yeah?
Yeah. And to do that is 2 pi FL,
Well done.
which is 2 times pi times 50 times 159.2 times 10 to the 3.
Hang on.
Perfect.
Excel,
To the negative
2
three,
pi
isn't it?
FL, 2 pi times 50 times 159.2 times 10 to the minus 3. And the answer to that is?
I think Taylor has the answer to that.
Yeah.
Oh,
Taylor
yeah,
does.
fine. I think Macaulay does, actually.
Yes. What did I get there?
50 ohms?
Yeah.
Yeah, something like that.
Perfect.
I got that wrong. 2.
Yep.
Oh,
Yeah.
So then
None of that,
we
please,
can
Connie.
And then
say
we have to find ZRL.
ZRL
R plus XLJ.
You can thank me for that one, boys.
and R is 40 ohms.
Yep.
XL we calculated as 50 ohms.
Yep.
Converting that to
Polar
Polar.
form.
equals what we got.
Taylor's got that one.
I can't do these polar ones. Computer.
You still ain't got that calculator, I suppose.
Coronavirus, you see, Mike. Can't get hold of it, can you?
Answer is
No,
Stocking
to be
up.
fair, one of the boys at work's got me on. I just haven't seen him in a couple of weeks. It's been away.
yeah. So the answer is someone.
64.
Yep. 64 what?
Yeah, what? Potatoes?
Ohms. Angle. Anyone got the angle? 51.35 degrees. Yep. So now can we find I coil?
How do we find I coil from that?
Right. Can you leave a whiteboard alone, please? Connor, how can we find I coil?
That's a good question.
Can we not use Ohm's law?
Yeah, we can.
We know V, don't we? That's
Yeah.
common. It's common to both components.
No,
And we
the
now know
resistance.
ZRL.
Oh,
Yeah,
Oh,
Okay.
we've done
So
this
it's-
before.
P over
240 angle 0 over the 64 ohms angle 51.35 degrees. We just calculated.
Yeah.
It's Nathan.
So that's 240 divided by 64.
You got the answer, Taylor?
Have you,
Three
Marcus?
points. 3.75.
Yeah.
Amps angle minus 51.35 degrees. Does that fit with civil? Yeah, inductive circuit, currents lag and the voltage.
Yeah.
Right? So that's calculated our current in the coil and what the phase angle is. Yeah.
Mm-hmm.
So next job is to
She called me. Yeah, yeah, she called me.
calculate the capacitor current, IC. How do we calculate that?
Taylor's got this one.
I see
Literally gonna come to
is
your hand, won't it?
the 240 volts,
Yes, there's the voltage.
and then it is the XC.
So do we currently know XC?
No,
So we need to calculate
XC
that.
is 1/2 pi FC.
Yeah.
I'm so good at this.
2 pi times 50 times 30 times 10 to the minus 6. Agreed?
Yep.
What do you get for that then?
I think Taylor's got that on.
Sorry, just hit my gong. Massive gong.
What? 0.1.
What?
0.1.
Yeah.
I got.
0.1.
Point one.
Yeah.
I didn't get that at all.
I got 106.1.
Yeah, that's well, I've got 106.1.
I think I may have hit the wrong thing there.
You might have done.
So we've actually got the same as the previous question.
What the?
Wait,
Yeah. Well, that
Yeah.
was the same values, wasn't it?
yeah. So then IC is equal to 2.262 angle 90 degrees.
Yeah, because we got IC is equal to 240 angle 0 over 106.1 angle minus 90. Like you say, we already done that. And we're
Yeah,
2.262 amps angle
that
90
was
degrees.
109.
Yep.
One minute.
Alright.
Macro, I bet that was your dog, wasn't it?
So, how could we go now? How could we now go on right, and
I'm back.
find
Welcome
the
back.
supply current? How could we
Supply
find
current.
supply current?
1 minute, 2 miles ahead.
If we look at this diagram again, VS, we now know this current and this one. So what method do you know of to find IS now that you know IC and IRL?
You have to change them into rectangular form, and then you have to add them.
Yeah, because that
Big Dom.
electrical law is called, Dom.
I don't know, but it works.
Yeah. Right. By Kirchhoff's
I didn't finish that.
current law,
It's hot.
IS,
Oh no.
yeah, IRL plus
The same with the Karen.
IC.
Yeah.
Yeah. Can we cut the guys? Can we cut guys? Can we cut the chit chat, please?
I think Macaulay was talking to his mum.
IRL was in polar form.
Yeah, so do we do
It's
Oh, wait, what is it?
3.748. Angle minus 51.35 degrees. We've got to add that to IC, which is 2.62262, angle 90 degrees.
when you add them separately?
No, we can't add them in polar form, can we?
Why not? Oh wait.
Well, we
yeah, you're right.
can if you do the sine rule, so we got to convert them to rectangular.
Yeah, got it. So we need to.
So you're going to convert these two
Going to be
to rectangular form and then add them together.
3.748 plus
Minus
50
53.
minus 51.35 J. Oh no.
No,
Plus.
you got to do conversion to rectangular. So you're putting in 3.76748
Plus.
angle minus 51.35 degrees.
Oh.
I'll get 2.341 minus 2.927 J for IRL. I'm going to add that to, I get 0 plus 2.262 J for IC. Now we add them separately. So we add these two bits together. We add these two together. Yep. What on earth is going on?
I think Macca fell down the stairs.
That is not me.
So we end up with an IS of 2.341. And then we've got to do minus 2.927 plus 2.262. So we end up with a small minus 0.655 J, which we can then convert back to polar form. I'll let you do that.
I think Mac has got that one.
Come on.
2.430. Is that right?
2.43 amperes angle
15.6.
minus 15. I've got 0.86, but
Jake coming in clutch. Good job.
yep. So that's the total current flowing. Yep.
Yeah.
Now we know that. Now we know
Yeah.
that.
Yep.
We can find the circuit impedance, can't we? So we know
You,
the voltage, we know the total current, so we can use those all for that. So ZT is VS over IS. That's 240, angle 0 degrees over what we just now calculated. 2.434 angle minus 15.86 degrees. Yep. 240 over 2.434. We get 98.6 ohms angle 15.86 degrees. Yep.
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 All agree with that. Good.
Yep.
Right. How are we doing for time on the old video? 21 minutes gone, halfway through. Right.
I'm sure
All
Adrian.
happy.
Yeah, Adrian did something where it said unlimited time on his lesson.
Yeah, I know.
I think you just splashed a couple pounds and, you know,
We know what Adrian's like.
unlimited time.
He had
I think he's in
unlimited
his
time, did
dressing
he?
gown.
Yeah, I don't know what he did, but it just popped up.
Didn't even need it.
Okay. Perhaps he paid, I don't know. Right. Moving on. So let's cancel that share for a minute. Save that. Stop the share.
If I share my screen,
No,
we can do a Minecraft. Let's
no,
play.
no.
I'll be back in a second.
Hurry up then.
I'm in the drop top.
You're going to bring it in.
Oh, Macca. Hello.
You're back. Right, guys. Are we ready?
I'm ready.
Yeah, I'm
Right.
ready.
Always ready.
Okay. Right. Ideal transformer. So the principle of the ideal transformer is considering this completely lossless, which is not true for a real transformer, but we may get onto that at another date. So if we make a winding around an iron core, like so, and supply it with an AC supply that's constantly changing, we produce a flux in that coil that goes into the iron core, and that flux has got some direction around there, like that. Flux, and a symbol for flux there. If we have a second, so that's called the primary winding, or the primary side, V1, we get current I1. That magnetic flux induces a current due to laws of electromagnetic induction that you did in science, such that we'll get, if we apply a load to the secondary winding, we'll get a current I2 flow through that load. Yeah. The EMF induced in either coil is related to the number of turns you put on the coil multiplied by the rate of change of flux. So the faster that flux changes, the more voltage you get. The negative to the sign is dealing with that Lenz's law of the induced current or the induced voltage opposes the change that's causing it. So what we then end up with is the ideal transformer equation that is here, where the ratio of voltage V1 over V2 is equal to the ratio of turns N1 over N2, which is equal to the inverse ratio of the currents, I2 over I1. So what you should always remember about that equation is the voltage and the number of turns ones are 1/2. The current is always the other way up, because you could equally write each of these as their reciprocals. You could write V1/V2 is equal to N2/N1 is equal to I1/I2, i.e. turn them all up the other way. Do you all understand that?
Yeah.
Yeah?
Yep.
Yeah.
So this over here is the general symbol for a dual wound transformer with iron core. Yeah. So it's a shorthand version of drawing what we've got here. And then when we talk about transformer rating, we don't talk about power in watts. We talk about the rating being in VA, which is short for volt amperes. The volt ampere is the rating of both the primary and the secondary windings. Therefore, the primary winding is 10 VA, the secondary winding is always 10 VA. And as you probably know, if we have different number of turns on the two windings, we can cause this transformer either to step voltage up or down. So if we have more turns on the primary side than we do on the secondary side, so if we have 10-1, so 10 on the primary, 1 on the secondary, we'll get, if we put 100 volts on the primary, we'll get a 10 for that, 10 volts out of the secondary. If we reverse that and say we have one winding on the, 1 turn on the primary and 10 turns on the secondary, we could then step up from 10 volts to 100 volts. However, you can't get something for nothing. So if you step up voltage, you'll step down current to keep the VA the same. So if you step up the voltage by 10 times, you will reduce the current by 10 times. And vice versa, if you step down the voltage, you'll step the current up. So all okay with that?
Yep.
Yeah?
Yep. Yeah.
Cannot gain power in a transformer. Right? There's a special name for this VA power. It's called the apparent power. But we won't get into that right at this time. All right. So moving over the page, I think we've probably got a problem. Yeah. Transformer has 500 primary turns, 3,000 secondary turns. The primary voltage is 240 volts. Determine the secondary voltage, assuming an ideal transformer. So time's getting down a little bit now. So what we'll do is have a go at that question, and I'll have a new room back up in about
Could you
10
just
minutes.
go down on your handout quickly a little bit?
No, because I've got the answer. Right? I'm too sharp for you, Macaulay.
What's happened is we can't quite see the bottom of the question.
Yeah.
Yes, you can. You've got it in your handout. All right?
Who wants a Dr.
Love-
Pepper?
Lovely, Mike.
Stop the share. Have a go at that question. And then we'll be back in. So I'm talking about 25 past.
I'm in a drop top.
At what time?